depends to the t, huh? And it depends to the mass. This is the maximum NA. In this case, how much will be N0? N0 will be N minus this NA here, maximum. Will be N minus VA Okay. When this condition will be meaningful, you know that N0 never can be negative number. Huh? N0 should be some number, any number greater than the 0. So in this case, you have to set this greater than the 0. Otherwise, it will be meaningless. If you put at this, set that this upper than the 0, you find that the N should be greater than this number. Huh? Of course, it depends to the mass of the boson resistance. And do you know what is interesting? I can replace all here with N. So it will be N H 2P M J 3/2, yes? Over V Kc/3/2 greater than 3/2. Can I write it that, because it seems that this quantity is very important, this number. Before this number, if N is less than that, N0 will be negative. It's unphysical. Only the case which is physical is that, and we take the maximum case, we take the maximum possibility. I mean, we take the maximum value of the excited state. First, we allow the particle to sit in excited state as much as they can. How much they can sit, how many particles, this is the maximum number. After that, you have already some more numbers you have, because N not finished. No. The other particle, they need to drop here. Huh? Let's sit all here. Even if you add one more particle, it will be sitting. Even if you put one more particle, all the particles. So, for a given N, the first the excited state will be filled, and after that it will come all to the to the ground. So this is, I call it critical. So I find that when T is less than some number, which this number depends to the total number of the particle, no? And also depends to the volume, then the situation happens. The situation is that all the rest, or all the remaining particles will be sitting in the ground state. And this state will be very heavy. And this is a new phase of the matter, because the equation of a state of this phase is not same as any other material. This is not either gas, this is not any other things like that. This is a different things. This is a state called Bose-Einstein condensation. So this is the schematic form of the Bose-Einstein condensation. So do you know what we will do? We can find N from here in terms of the TSC N. And back to this equation, and just replace it N versus the TSC. And this is actually already have a T. So just a little bit mathematics. So I will give you this as a small task, just to take this N from here and put this here. So in this case, we will find a more beautiful equations. The equations will be like that. N0 over N will be 1 minus this 3/2 maybe will change for different systems. For this system, non-relativistic and the non-interactive bosonic gas, this appear 3/2. And if you make it plot from that, you can see that what is the situations. And I don't want to talk what happened for the pressure here because all these mathematical states existed here. The thing is that the pressure will be changed significantly when if I take this as an n0 over n, the portion of the particle in the ground state over the total. Yes? How many of the particle will be sitting in the ground state? And here, if I set a t over t0, tc, as long as t less than tc, n0 over n is less than 1. I don't know how to write it that. Yes. So this is the graph for that. When t is greater than the t0, of course you cannot, the n0 will be like not very big number, so n0 will be any other numbers. So I want to write one more equation here. So this is the n0 over n, no? So n0 over n will be 1 minus t over tc over 3 over 2. So NAE was n minus n0. So NAE over n, what is NAE? 1 minus NA0 over n. So it will be t over t0 over 3 over 2. In the book they plot all together. So this is n0 over n, and then the other graph, which started with t when t is less than t1. When there is less than t1, it will be below this line. Yes, it will be like that. So this is n here. So this is the n0 over n, and this is the n0 over n. This is there are the functions of the time, temperature. You can plot the pressure, you can plot the thermal energy, and finally to know that a phase transition happened, you needed to check the entropy also, but I don't do that now because it will be very, it takes time from us and we won't just finish it. So the things which happen here is that something about the phase transition and what is the real phase transition and those things. But the mechanism was the one which I explained already is the mechanism of the Bose-Einstein condensation. So, and it happened I told you, only in the bosonic system with the mass, because you see that to define the critical temperature, you need to have the mass. So if the mass is 0, so it doesn't happen. It happened for another type like relativistic, ultra-relativistic. For example, if you just change this to relativistic, so relativistic boson, when energy is radical P squared C squared M squared C4, M is the mass. You can repeat this, I actually repeated that before in the past. You can find a paper that, very old paper, which they studied the relativistic case of the Bose-Einstein condensation. You can repeat all the calculation by that. It's a little bit hard. And for ultra-relativistic also, you can have these equations, E equal PC, that's you can do. And for ultra-relativistic, you can have also the Bose-Einstein condensation. And because all happen in the low temperature, so, and because we know that the average temperature of the whole universe is almost very low temperature, 2.7 degree Kelvin, no? So the question will be, with nobody studied that before, I don't know that, is it possible to have the condensations in the large scale cosmological scale or not? And if happen, what's the evidence and what is the result of that? So because condensation is a new type of the matter, so maybe it will be a candidate for the dark energy or for the dark matter, or dark matter, I don't know for the dark matter, but maybe it's for the dark energy. So it can have some application in cosmology, definitely. So I think this information is enough for you to follow the literature also about the Bose-Einstein condensation. So, but this is not the all. This is just a non quantum field theoretistic version of that, because this Bose-Einstein condensation can be explained in terms of the field theory. You need to label the particles which are responsible to do that. So there is some theory about that. You can read it yourself.